Now the rate at which salt is flowing into the container is 10% of R. So the inflow, or the input of salt, is at rate 0.10 R. Now at this point you might have an objection that to my interpretation in terms of gallons per minute and pounds per gallon. You'd have a valid objection here. We're not going to worry about that right now. We're just going to say, okay, the input of salt we can consider to be 0.10 R, and we can adjust that for units in any way we set up the problem. So let's not take the pounds per gallon and gallons per minute quite literally. Just trying to give you an idea of how these inputs and outputs might be measured. Okay, so the input is 0.10 R. So the rate of change of Q is 0.10 R, that's what's coming in, minus Q over V times R. And that leads us to the differential equation, dq dt equals 0.10 R minus Q over V times R. Of course, we can factor the R out and do other things to simplify the form of the equation, but we understand that this is an equation that tells us Q is changing at a rate that's equal to the input rate of salt minus the output rate of the salt. This equation we can see can be rearranged into dq dt plus Q over V times R equals 0.10 R, and that's going to be a linear non-homogeneous equation. We can represent the situation in a graph of Q prime of t versus t, the rate at which Q changes versus t. The rate at which salt enters is constant. Matter of fact, that's now seen to be 0.10 R. The rate at which salt exits, now that's not actually right. This should be the rate at which the amount of salt changes due to exiting, but I'm not going to change the wording here. You still get the idea. Is going to be negative. The greater the time, the greater the concentration in this vat. And the greater the concentration in this vat, the more salt is going to flow out. So we have the rate at which salt enters, and we have the rate at which salt exits. If we take a little bit of liberty with the words, and we see that we have a net rate of change of salt that's decreasing with time. Up here in the equation we see that if Q increases with time, then this right hand side is going to decrease. The bigger Q gets, the bigger the negative gets, and the smaller will be dq dt. So that's consistent with the graph. We have this net rate of change. Now we have the question, and we'll leave as an open question until we solve this equation. The question is this a linear function? I've drawn it as linear because I'm pretending not to know. Is this net rate changing at a linear rate? Or does it change in a way where this is concave down, which would make this? Would that make this concave down or concave up? How would the concavity of one graph affect the concavity of another? So there are a lot of things to think about here.